Alright, hi everybody. In this video we're going to be talking about evaluating functions and how we evaluate functions. First thing I'd like you to do is take a few seconds, pause the video, talk to your partner next to you, and try and answer these two questions to each other, talk about the answers to these questions. And then when you're finished, unpause and we'll pick up with today's lesson. Alright, so pause now. Alright. Welcome back, everybody. First question here that we were reviewing, what is a function? Can you give an example? A function is a relation where each input, or x value, is paired with, at most, one output. Or y value. And you've seen all kinds of functions over the years. When we say, can you give an example, y equals x squared, that's a function. Y equals the square root of x, that's a function. Y equals 1/2 x plus 4, lines, parabolas, square root functions, there's all kinds of functions that we've looked at. There are, literally an infinite number of possibilities for this. Can you give an example? How about not an example? Not an example? Something like this, x squared plus y squared equals 4. Not an example of a function. All right, question 2, which of the following graphs is not a function and why? At some point in time here before, we've talked about the vertical line test. Imagine passing a vertical line over these graphs, and you can quickly and easily tell which one is not a function. B here is not a function. And the reason why is because there are x values that are paired with more than one y value. More than one y value. A quick way to say it with a graph is that this fails the vertical line test. And the reason that it fails the vertical line test, if you imagine running a vertical line over the graph B, for instance right here, at this x value, we have two different y values. That makes it not a function. If we run a vertical line over graph A, it never hits more than one point at a time. If we run a vertical line over graph C, it never hits more than one point at a time. Okay, so a quick little review of functions for us there. Let's get into the meat of today's lesson, function operations. We have our first 4 function operations, which we're going to talk about. They're all pretty straightforward. The sum of two functions, if I take the sum, f plus g of x, I get that by just adding the individual functions together. So f plus g of x is going to be equal to f of x plus g of x. Pretty straightforward. The difference of two functions, f minus g of x, is going to be the difference of those two functions, f of x minus g of x. The product of two functions is going to be the product of each individual function. So f times g of x is equal to f of x times g of x. And the quotient, f divided by g of x, is equal to f of x divided by g of x, as long as g of x does not equal 0. So we're going to have restrictions whenever we take a quotient, or we could potentially have restrictions. We're not always going to have restrictions, but we could potentially have restrictions whenever we take the quotient of two functions. So we need to be aware and pay attention to that when we do that. All right, so those are the 4 basic function operations: sum, difference, product, and quotient. We're going to go ahead and work through some examples now utilizing these operations. So let's start with example 1. Given that f of x equals 2x plus 7 and g of x equals negative 3x plus 5, we're going to find the following. Part A, f plus g of x. So from our rule, f plus g of x is equal to f of x plus g of x. And I highly recommend to you, when you're putting these functions into the operations to figure out the sum, difference, product, quotient, you can get away with it in the sum, but I highly encourage people, when they substitute functions into these operations, to put the functions inside of parentheses. This will be really helpful for us, especially when we do subtraction and multiplication. With addition, it's not such a big deal because, since I'm adding these things, I can just go right ahead and drop the parentheses from them in order to simplify. And now we're going to combine like terms, and we end up with the sum being negative x plus 12 for part A. Part B, f minus g of x. So that's going to be f of x minus g of x. And here the parentheses are going to be a little bit more important for us because they're going to remind us to distribute that negative sign through all of g of x and not just the first term. So we're going to go ahead and write f of x minus g of x. We substitute the functions in. We do what we need to do to get rid of the parentheses. Distribute the negative sign through the second set. And now we combine the like terms, and we end up with 5x plus 2 as our result. Okay? All right, on to the next example. Example 2. Given that f of x is equal to negative 2x plus 3 and g of x is equal to x plus 4, we're going to find the following. All right, first of all, f times g of x. Based off our rule, that's going to be f of x times g of x. And now I substitute the functions in, negative 2x plus 3 times x plus 4. And now we're going to multiply this out. We've multiplied binomials together before. We multiply our first terms, negative 2x times x is negative 2x squared. We multiply our outer terms, negative 2x times plus 4. It's going to give us minus 8x. We multiply our inner terms, plus 3 times x. And we multiply our last terms, plus 3 times plus 4 gives us plus 12. And then we're going to combine our like terms. And there's our answer. All right, next. F divided by g of x. Again, that's going to be equal to f of x divided by g of x. And in this case, when I'm doing division, I don't normally put them in parentheses because the division bar is kind of an implied grouping symbol. It kind of implies that we're putting the numerator in parentheses over the denominator in parentheses. So I've never put parentheses around my functions when I do this because that grouping bar separates off the two functions. And so we end up with f divided by g of x being equal to negative 2x plus 3 all over x plus 4. This is a quotient. We need to pay attention to the restrictions. We've talked about this before, of course. X cannot be equal to negative 4 in this division because that value of x makes our denominator equal to 0. All right, continuing on. Well, earlier in mathematics, you learned the 4 basic operations: addition, subtraction, multiplication, and division. And we had those same 4 operations for functions. Well, when we start talking about functions, there's a 5th operation that we need to be aware of and that we need to know how it works. And that is what's known as the composition of functions. And when we do the composition of functions, we are performing those functions in a certain order. We're going to do one before the other. And the notation tells us which one comes first. There's 2 different ways you might see this notated. What we refer to the old school notation, fog notation, f with a little open circle of g of x. That's red, f of g of x. Or we tend to see this notation in the modern day much more than we did when I was a young man. And this is just f of g of x. Now, what does this mean? Well, what we're going to do is we're going to take x and we're going to put it into the function g. That's what this inner part means. And then we're going to take the result of that and we're going to put that into the function f. And we're going to do tons of examples on this between this video, and we're going to do a second video where we get into and do some more examples of composition to get us started. So we say this, f of g of x. If you ever see this, that's what you should be saying. This is f of g of x. We put x into g, put the answer into f. That's what it means to take f of g of x. Please note, f of g of x does not mean the same thing as f times g of x. This is a very common student error. If you see the open circle, this means composition, which is f of g of x. If you see the little dot, this is multiplication of the 2 functions. That's f of x times g of x. All right, let's get ourselves started here. Example 3, given the functions f of x equals 3x minus 2 and g of x equals negative 4x plus 1, we're going to evaluate the following. First, we're going to find f of g of 2. All right, so first, I'm going to break it down a little bit in these first couple of examples, and then I'm going to take it to a more advanced level as we go. First, we're going to find g of 2, since that is the inside portion of our composition. When we're evaluating compositions, we always start from the inside and work our way out. So first we're going to find g of 2 here. So we're going to take our function for g and substitute 2 in there. And that's equal to negative 8 plus 1. And so g of 2 is equal to negative 7. All right. That means now we're going to replace this g of 2 right here with a negative 7. So our next task is going to be to find f of negative 7. And so we're going to go ahead and we're going to calculate the value of f of negative 7. So we'll put negative 7 into f in place of x. We'll do our calculations. We get that f of negative 7 is negative 23. And therefore, we've worked our way through this, f of g of 2 is equal to negative 23. All right. Part B. Now this time it's written in fog notation. We're finding g of f of 1. You certainly want to think about this as being g of f of 1, like so. So we're going to start from the inside and work our way out. So our first task is to find f of 1. So we're going to put 1 into the function f in place of x. And 3 times 1 is 3. And so we find that f of 1 is equal to 1. All right. So now we've found the inside here. We're now going to substitute that into g. So we're now going to find g of 1. Find g of the result of our original function operation. So g of 1 is equal to negative 4 times 1 plus 1. And from here, it's just a matter of doing the calculations. And so g of f of 1 is equal to this final result, negative 3. All right, that's where we're going to call it quits for this video. We are going to come back and do some more examples in a second video. You can go ahead and cue that up as soon as you get done watching this one. All right, everybody, have a good rest of your day. See you next time. Bye-bye.